Only 2 levels left until we can start on CPU architecture, leading up to a working computer, which is probably the most exciting of the levels. I have no idea how I'm getting from memory piece to a working computer in this few levels, but we'll see. We can start with Little Box, the level we took a look at last time, but decided to leave for later. Well, now is later, and it's time to actually do it. Alright, the statement is fairly simple. There is, as always, a slight issue with what happens when I'm not saving and not loading what the outputs are. The output needs to be, but I expect this to be fairly simple to figure out. Now, yeah, and also it's not clear what I'm... Whatever, yeah, it's fine, because we have the load pin down below, and it's gonna zero out or disable all the outputs that are unwanted, so this is good. Now, full disclosure, I've actually already started taking a look at this level, and after maybe 5 minutes I realized that my recording was not going well, so that was broken and I had to reset. But pretty much all I've been thinking about is just the issue of addressing. So I have these 2 address pins, right, which select between A0, A1, B0, B1, right, AB01, which are intended to select between my 4 bytes of memory. I need 4 bytes stored for this problem, right? I need 4 different bytes of memory, save and load, and I need to be able to address them. Now, obviously, these 2 registers being decoded into 4 locations, 4 different separate outputs, is exactly the problem of a 2-bit decoder, right? So we did have a 3-bit decoder and a 1-bit decoder previously, and now we need a 2-bit decoder. And of course, a 3-bit decoder would work for a 2-bit decoder just fine, right? You just pipe 2 bits into it, and the third one remains 0, and that's enough. You will select between 4 of the first 4 pins. However, it turns out the 3-bit decoder level is actually later in the tree than this level, right? We get to this earlier than we get to the 3-bit decoder, or rather they are parallel, they're at the same depth. And while we do get a 3-bit decoder for completing this, we do not actually have it in this level. We cannot use it. We only have a 1-bit decoder, right? So, yeah, unfortunately this means that I'm probably gonna have to build something, well, not probably, definitely, I'm gonna have to build something resembling a 2-bit decoder in this tiny box, in addition to all the other logic that will happen in here. And for that, I've been wondering if I can finally improve this crazy machine somehow. Now, another piece, I don't know, I'm just gonna say it again, full disclosure. I am recording this video before before the previous one was published, so I have not yet seen any comments on this. So I do not know how to improve it, but I've noticed one important part, well, not necessarily important, but one fairly useful realization. Here's the thing. I have right here 3 1-bit decoders at the start, right? I have a 1 and not 1, 2 not 2, 3 not 3 inside of here. So I can kind of reduce this structure to 3 decoders like so. Now that's not actually gonna improve my NAND score or anything because a decoder is literally just that inside. But I think that might be helpful to save space. Although, I'm not even sure. It doesn't even take less space, but still, I feel like using these decoders is gonna be a better way. It seems nicer, so let's apply them here first. So I pipe. This is gonna be this is not gonna be as nice of a wiring, but well, yeah. Okay, I'll be back once this is all wired up. Well, I'm not gonna bother too much with trying to make this perfect. So this is the thing. Let's check. It's not working. Why are you not working? Why is this not... Did I wire it wrong? I think I wired it wrong. BRB? Yeah, right. I think I wired it inverted, so I just need to switch these up. Just replace green with red and red with green. Like so. Now let's check. Yep, perfect. So, and this also has a slight logical improvement, I guess. It makes this schematic slightly more intuitive, I would say. If you take a look here, I don't actually remember how I explained it or how I came up with my original solution, but this single element, 1-bit decoder, if we start from the third bit, the most significant bit, this decoder decides whether we're in the first or the second half of our output, right? So basically, this decoder decides whether we're going up here or up there. And once we've got this decoded, we already know that we're definitely in here or in there. Now, once we know that we're in one of these halves, we take a look at the second decoder, and this one decides which half of the half we're in, right? So if you take if we take a look at the truth table, right? If we know that we're in the first half, then the second one divides the half in half, so this is fourths, and it decides whether we're in up or down. So if we know that we're, for example, up here, then this guy will decide between these two pins and these two pins. And the same goes for the final one, the small guy. The first two decided in which fourth we are, and the final guy decides if we're up or down in them. And this is, of course, reflected in this wiring, right? If you take a look here, for example, this final decoder, it only connects to ANDs in the first half, so it leads into here, while this is completely unconnected. And the same goes for everything else. If you take a look, for example, at the green line here, it enables the ANDs down below, so the second half, while up above it has nothing. So this is kind of neat, and I actually really doubt that it's possible to make this any nicer. Still, I will be excited. I am excited to see if there's any suggestions. So that's that, and I think we're just gonna have to rebuild this, or at least partially rebuild this. Rebuild half of this pretty much for the 2-bit decoder for our little box. We need 4 bytes. So let's avoid the 4 bytes for now, I think. Let's put our addressing logic somewhere down below. Right, I'm gonna try to think ahead here, although I'm not thinking too far ahead, am I? And we have 2 decoders that will lead into 4 ANDs. We have 1, 2, oh goodness me. 1, 2, 3, 4 ends. Oh my. Oh, this is... Okay, maybe I rotate them? Maybe I think I might want to rotate these ends so that, yeah, But I need... How many spaces do I need to leave down below? Well, let's see. 4 ends. And then we wipe this up. We connect it all up. How do I do it? See, now I'm confused by my own rotation. So, the second guy, if the second guy is 0, then we're in the first half, right? Which means that we're gonna go either here or here. Well, this leads either here or here. And now this guy just selects between first and second in each. So if this guy is off, then first, otherwise second. And again, first. Okay, I need colors. I desperately need colors. How do I want to color this? Okay, so let's call this guy red and let's call this guy green. I don't know, for some reason I like to use red and green. So down below is going to be red. And this guy is going to be green. So what am I doing here? Like so, right? And then like so. I'd say that's decent. This looks decent. Let's try and check. So, yep. And then, yep, perfect. This is working. Now we need to add our 8 or our 4 memory locations. So how are we gonna do this part? Definitely they're gonna need to be connected to each other. So we have a single output. Now we have a save and a load. Don't I just connect save, load, save value? Wait, so save, load. Okay, so save value. This is the easy part. We have the same save value for all of them. So I might as well just connect this all up. I'm completely disregarding the recommendation, the suggestion, or whatever they call the advice about using right angles and stuff. So actually, this would be better with right angles, like so. Sure, kind of. And now, I think my save and load... No. Yeah, I will need to... So, load... I am free to just always load. So I'm free to always load from each one of them by their address, which is fine. So I load from the first one with this, I load from the second one like... Wait. Yeah, I load from the second one like so. I am kind of ditching all niceness for now. Right, I load from the fourth one like so. Wait. Yeah, see, this is confusing. I load from the third one like so, and I load from the fourth one. I cannot load from the fourth one anymore. Okay, I think I might want to rotate this whole contraption upside down, or, you know, 90 degrees clockwise. I'll do that, and I'll be right back. Alright, I'm done with this. rotated this up, just removed all the junk from the middle. And by the way, an interesting realization I've had while doing this, it's actually completely irrelevant to me how I wire this up. So I am trying to make this nice and intuitive, assuming the count is A0, A1, B0, B1. You know, the ordering is A0 is first, then A1, then B0, then B1, assuming that the number is the less significant digit and the letter is the more significant digit. And then I try to count upwards. But really, all that matters for me is I can decode this in any kind of, you know, in any configuration I want. So I don't have to go up, down, 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 and I can rearrange these memory cells in any way I want. And it's all gonna be exactly the same. It's, could you say it's gonna be like topologically equivalent or something? I don't know. But yeah, so I did this, and I also replaced green and red with light blue and darker blue for least significant and most significant. I don't know. It feels like that would probably make more sense. Now let's continue with the rest of the problem. We are saving the same value always, so it's fine to do this. However, something I need to select is come again. Right, so I need to wire up all the loads. But actually, let's first start with the saves, because the saves have to be ended with their corresponding with their corresponding signal, their corresponding address. So this is gonna be save 1, and it's gonna be true if we save and we save 1. So let's wire it up. Let's say our save line is green. Let's wire it nicely like so. And then let's say, right, I need to actually connect it to something. This seems okay. And now we have our outputs. I don't think I'm gonna color them. 1, 2, 3, 4. Should I offset this? Sure. Why not? Like so. Now this is our... Oh, yeah, right. So, yeah, this is the reason why I decided to build the ends first, because I also need to pipe the raw value into the load. Which, how do I do that nicely? I guess I just space these ends out. Like so. Is this what I have to do? Is there a nicer way to do this? I don't know that there is. Yeah, well, whatever. So I think we're pretty much done here. So we load always. It's fine to always load. It's fine to always load. But we only save when we save. Like so. And now this is our output, which again we can join everything up and pipe into the out. And load doesn't matter to me at all. I just pipe it into there. Let's check. Wait, what? Oh, I forgot to connect the actual save value. Sure. I will improve this slightly once this is done. Cool. In our advanced civilization, forcing prisoners to do extremely menial tasks is slavery and is technically illegal. That is why we instead had our intern create the 256-byte version of your component. 256 byte. Oh my goodness. Oh my goodness. 256 byte. Can you imagine this? As a 256 byte? Oh my goodness. Can you imagine this? As a gigabyte. So my 32 gig RAM in my computer. Oh, that is some serious slave labor. Wow. Can you imagine 32 gigabytes of this? Alright, I'm gonna clean this up slightly, and I'll be right back. Cool. I actually ended up feeling comfortable enough in this box to let it breathe a little. So here, for example, I actually spaced these guys out just because it was nicer. So yeah, that's my solution probably. You know what? I'm gonna make this even, I'm gonna add even more right angles by removing these ones, so BRB. No, I decided it looks better with some non-right angles still. But yeah, at least these intersections look nicer now. Cool. I'm very happy with this one. Turned out pretty nice in my books. And we can proceed. 256 byte RAM. Incredible. Program. Goodness. Alright, logic engine. I feel like this is a final test. Oh wow. This is actually a huge playing field. Okay. Or was I just zoomed in too much? That now this feels like a lot? No, this still seems like a lot. Okay, create a device that can OR, NAND, NOR, or AND two inputs. The third input will be... Oh yes, this is what I've been wondering. An instruction is just what we call the number that determines what to compute. So instruction 0, 1, 2, 3, or NAND, NOR, AND. Is you can't move the red components. Also, you can't move the red components in this level for reasons that will be revealed later. Wait, why is... This is a byte. Goodness, this is a byte actually. NAND, NOR. Oof, that's a bit more... It's a bit more complicated. But still, I think we're fine. So, yeah, this is what I've been wondering. This right here is the introduction of the von Neumann architecture, is it not? Where the data can determine what instructions are performed. That is, of course, the foundation of all, I think? Well, at least an absolutely dominating most of modern computers. And this is what I've been wondering, how soon was I going to get to this kind of architecture? Because I believe, and I haven't actually thought this through, I never encountered these two things in the same sentence, believe it or not, but a Turing machine does not implement a von Neumann architecture, at least not necessarily. Right, you can have a program in a Turing machine that is just hard-coded into it, into the states, into the transitions. Although it is still capable of interpreting instructions from the what's it called in English? The thing on which the data is written in a Turing machine? The ribbon? I don't know what it's called. So yeah, still I was wondering if we were going to get to a point where basically I could implement anything using gates, but in order to implement something different I would have to put other gates, and that would be called Turing Complete. Or, well, again, if that was Turing Complete, then I could inside of it implement the von Neumann architecture. I'm just thinking out loud here. It might actually be wrong, but yeah. Okay, the instructions are clear, I think. Or, NAND, NOR, AND. These are my two inputs, right? Wait, what? Oh, I need to perform the byte OR and byte NAND. Okay, but I do have them, right? No? Oh, come on. Seriously, I don't have the byte NOR, byte NAND? What are you talking about? This is ridiculous. I'm gonna have to re-implement this stuff again? No, you should have given me a gate. Although, I don't know. Maybe there's a reason why they don't. We'll see. Okay, so how do I do this? I mean, seems obvious to me, to be honest. Right, I just implement the 4 gates separately, like I would put them down here somewhere, whatever, especially since I have to actually build them out of byte splitters. I perform all 4 operations, always. And then I have a mux, maybe, or a bunch of switches. Do I use muxes or switches? Input 1, input 2. Huh, this is another curious thing. Could I perhaps use muxes here for my instruction decoder? I will have to re-implement my 4-bit decoder. In fact, I'll probably go back and copy it. I think that's what I want. I don't think I'm gonna be... Yeah, I think all I want is just to split this immediately, pretty much, and just decode the first 2 bytes or 2 bits. Right, as soon as this one glows. Yeah, so I only expect the first 2 bytes, the first 2 bits, so I don't care about the rest. For now, I expect there to be more instructions than just OR, NAND, NOR, AND. So yeah, I just decode this into 4. And either I switch my 4 outputs using these ones, or I somehow use a mux more cleverly. I'm gonna have to think about this for a moment. But yeah, first I'm gonna go off and implement all 4 byte operations, and I'll be right back. Okay, so I just went back and copied my solution for the 8-bit OR, pasted it 3 times, replaced the gates with NAND, NOR, AND. That's exactly what I need. So this one I already have as a single gate, or I have a NAND, I have a NOR now, and I have an AND. So these are all 4 of the actual computations I need to perform. And I think I just pipe both of these into all of them. I expect this to be a huge unclean contraption in the end, which is uncool. But I don't think there's any better way to do this. I am slightly, again, what's the word? Self-conscious? I don't like this 8-bit logic gate design. I feel like there's a nicer way to do this with some kind of intersecting pattern of right angle things. Which, I mean, I could just go and rotate 2 of these, put them side by side and have a huge matrix like so. But it's not actually going to be any smaller, right? In fact, it's going to be larger. And it's gonna look bad. So yeah, I don't know. I remember, I think I did mention this in the original video when I was first trying to make these. I did try to implement something like this. Right, there is the idea that one only needs to go into 1, and then 128 can go over here somehow, or something along these lines, right? So that they can actually share these, whatever you call them. But this doesn't quite work, because I actually need this inverted. Which, actually, now that I think about it, I might just want to invert this thing by hand. Kind of like so. You know? Just do a crazy invert bit. And then... You know what? I'm actually tempted to do that. Should I? Should I? I will do this. I will do this. I'm curious how this is gonna look. I'll be right back. Guess this has the right to exist. Does it? It seems fine. I don't exactly understand why. Well, whatever. So, I hope these wires are not all tangled. Actually, oof. I'm afraid they might be. Let's try powering 1 on. No, it seems to find its way. It seems to find its way. Yeah. Huh. Cool. Cool. So yeah, I think this has the right to exist. It's not smaller. It seems about the same size. Yeah, it's even bigger, really. And it is not nearly as compressible as this, because this guy I can really squish if I want to. Right, I can just boom. That's it. But you cannot tell anything that's happening here. But it should still work. While this is not compressible at all. I cannot squish this in any direction. But a nice thing about it is that it has inputs and outputs up top, and the output is up top, as opposed to going left to right. Which I think can kind of work for my current problem. So I'm just gonna apply these out of... just because I think it's cool. If you like it, that's all. So I need 3 of them. Except the second one is NAND. Oops. Third one is gonna be NOR. Okay, I'll do this and I'll be back. Alright, so this is what we have here. And now what I'm gonna do is I'm gonna pipe both of these inputs. So let's call them green and red. I'm gonna pipe them both down below. And so this is gonna be my input 1. Are any of these gates, they're all symmetric, aren't they? Wait, can you even have a... I don't know, I don't care. So let's pipe this guy like so, and like so, like so. I will clean this up later if I feel like it. And the other guy will pipe into here, and into here, and into here, and into here. That'll be that. And now we'll have our outputs. We'll have output 1 going this way. I don't know where I need them yet. So let's just leave them unconnected for now. And let's see what I can do about these instructions. So, like I planned, let's just split it up immediately. Yeah, I think I'm gonna put maybe the logic up top. So the actual thing is calculated at the bottom and the logic happens up top. I am given a lot of space here, so... Alright, so we have 2 bits. Let's go back and copy our solution for the little box. This is gonna be our decoder. Like here. We are decoding these 2 bits. Which is first and which is second? Alright, this is second. This is first. Okay, I don't care for now. Well, the niceness of all this. I could also squish these, but let's see. Now, depending on what gate we have, we need to pipe our output. Is the mux... Oh, the mux output pin is not gray. See? The switch output is gray. And I definitely want gray output because I want to combine 4 different options. So I am just going to use switches, which means I put 4 switches. I think I might even fit this in between them. Will look semi-nice, right? And then I pipe 4 switches. Can I? No. Then I pipe the 4 switches into the output, like so. Right, and I can... how tall is this? Okay. Yeah, so that's the idea. I put these into there. Gonna have to... Okay, I'll rewire this all up real quick and I'll be back. Okay, so disregarding all the mess, I think this is the solution. This should work. So we have our 4 operations, we have our inputs messily piped into all of them. We gather all the outputs and we put the outputs into a 4-way switch. Which... Slightly weird why this is glowing while... Oh, yeah, okay. Yeah, so the green pin means we have a non-zero byte coming in, but they're all disabled and the selection happens via a 4 or 2-bit decoder, just like so, and by splitting this byte into its constituent bits. So let's test this. It works. And now we get an 8-bit AND, 8-bit NAND, and 8-bit NOR. Thank you. So they really wanted me to build some huge things, I guess, so that I learn how to manage space, which I am gonna do now. I'm gonna try to make this look neat. I've been thinking of actually replacing this ore with another huge contraption like this just for symmetry. And I'm gonna think of how I'm gonna deal with these wires. So, BRB. Something like this feels alright. I mean, of course, there's always room for improvement. This up here situation does not look great. I think they may have intended for me to build it separately somewhere and not in the middle. Just have a neat main, you know, have a separation of concerns and have a different function up there. But for now, this feels okay for me. Right, we have our input 2, piped as red, we have our input 1, green. They passed into all the operators and combined as before. So I think that'll be it. Maybe something like this, so that the wires don't intersect. Yeah, I think that'll be it. We're good. And we are ready to start learning CPU architecture. Arithmetic engine. Registers. Well, having done the logic engine, I would expect arithmetic engine to be fairly simple. And registers sound like more memory. But that I will do next time.